So, this example is showing you guys kind of that shortcut method, and I know you guys like shortcut methods, so I will teach it to you. Well, I tell you the algorithm up here, but honestly, we don't follow the algorithm very closely oftentimes because as soon as we see a path to the solution, we just take it, okay? So if you are first learning how to go through, it makes sense to refer back to the algorithm, but if you're getting a little bit more used to it, you can stop using every step of the algorithm. So, given the circuit shown with voltage source Vs and output VL, what is the transfer function from Vs to VL? So that is from the voltage source to the voltage across the inductor. And then, without transforming the source, find the transfer function from Vs to IL. And then an alternative route up that is to transform the source, as we'll do in C, and find the same transfer function. So, we're going to see sort of all of our methods, or all of the sort of tricks that are involved in our shortcut method here come in with this example. So that's why I developed it. So for part A, what is the transfer function Vs to VL? So we're looking for this divider rule thing, right? We want to transform this circuit into either a current divider or a voltage divider, since we're working with an electronic system, right? So either an across variable divider or a through variable divider, which for an electronic system is voltage or current, right? So a voltage divider would be perhaps our best candidate for a couple reasons. We're interested in voltages. So when we're interested in voltages, a voltage divider gives us those directly, right? It works in voltages. So if we can use a voltage divider, that would be preferable. We don't have to transform anything at the end, right? So we're looking voltage divider. We're interested in our output element is L, right? And we want to combine things to make the circuit look like a voltage divider without combining away our output variable, right? Our output variable is the voltage across L. So I hope you guys can see that if you combine L and C together, we have two impedances in series, the voltage applied across, so we have a voltage divider, which is great. But are we going to lose our output variable when we combine these two elements? Yes or no? What do you guys think? No. That's correct. No. Why is that? They already share the same voltage. So even after you combine them, they're going to share the same voltage. So you lose access to the current through L, which is problematic in B and C, right? But in part A, we only care about the voltage. So we can go ahead and combine away, no problem, right? So let's try that. Let's combine these, and that would be an impedance. And the R is an impedance. So we immediately have the voltage divider equation, right? So let's just one-liner it again, right? You guys love it. So VL, the voltage across inductor L, is equal to the impedance of the equivalent combination of these two, which they're in parallel, right? So in terms of ZC and ZL, it's just a parallel impedance combination. So we'll do ZL, ZC, either one. ZL, ZC divided by, I didn't give myself very much room there, did I? ZL, ZC divided by ZL plus ZC. So that's our two-element parallel combination of impedances, right? And then we divide that by, we have the same impedance again, ZL, ZC, divided by ZL plus ZC, plus the other impedance, which is ZR, right? Now we've got the impedance of the element we want the voltage across, divided by the sum of all the impedances in series. Now we multiply that by the input voltage, right? Yes. And it's like we're practically there. We just need to sort of simplify a little bit. So if we simplify, so I guess the first thing to note is let's immediately, and we'll start to do this before, in our first step once we get more comfortable with it, but we can immediately divide by Vs on both sides, right? So we get VL over Vs equals, and this is our transfer function. VL over Vs is what we're looking for. So now on the right-hand side, we have all these impedances to throw in and simplify, but it's done. We like wrote down our transfer function like no problem, which is awesome. It's powerful. So let's drop this denominator down. You can think of it as multiplying numerator and denominator by ZL plus ZC, canceling ZL plus ZC in the numerator, and canceling this one in the denominator, leaving us with ZL ZC plus ZR ZL plus ZR ZC. We'll distribute immediately because we like to write down fewer steps, going against everything your algebra teacher taught you. Just we ain't got time for that. We have lots of stuff to do. So ZL times ZC. ZL is LS, ZC is 1 over CS. The S is cancel, right? So we just get L over C, L over C, plus ZR is just R, LS plus ZR is just R, divided by CS. So let's simplify that a little more by multiplying the numerator and denominator by CS. That leaves us with, I'm just trying to get rid of fractions here. There are different ways to go about it. You can also try to put it in standard form where the denominator's highest term in the polynomial of S is 1. You can do that too. It's really kind of up to you, unless it says specifically to put it in the standard form. Whatever looks simplest is usually the best way to go. So if we multiply numerator and denominator by CS, we cancel the C, we get the S remaining. On this one, I'm going to move, this term is going to turn into an S squared term. I'm going to move it to the far left because it's the highest order S term. So we're going to have RLC S squared plus, we're going to have, this one is going to have the CS cancel, so that's the lowest order one. This one has this C's cancel without the S, so we have LS remaining, plus, and then this term, the CS and CS cancel, so we just left with R. And that's pretty dang simplified, and that is our transfer function. So pretty sweet. Didn't have to do any elemental equations or continuity equations or normal tree or any of that stuff, right? We just, bam, got ourselves a transfer function. Pretty nice method, very powerful to use, especially if you're just interested in a specific transfer function in the system. Okay, so part B asks us to find the transfer function from Vs to IL, which we observed in the voltage divider thing we just did. We lost access to IL. However, since we've already got ourselves, well, I say specifically without transforming the source. So you could say, let's transform the source, let's do a current divider. We'll do that in part C. But in part B, I say you can't transform the source, so we got to choose another way. To choose another way would be to use our result here, which gives us a transfer function from Vs to VL, but we have an elemental equation for L that tells us how to transform from VL to IL. So we can just use this, plug in our impedance Laplace version of our elemental equation, and get our solution just directly. So it's pretty nice. So let's do that. So we know from the elemental equation for L that VL in the Laplace domain is just equal to, so IL times ZL, right? Okay. And so we're interested to know what IL over VS is, so we could just plug this in to the previous expression and have essentially just to divide both sides by ZL, and we're in business. So let's do that. So using VL over VS from A, we have that VL over VS equals, let's just plug this in, so IL ZL over VS. So that tells us that IL over VS is equal to 1 over ZL times VL VS, right? So this is the result that we have from before, and we can just plug in our impedance for L, and we're off to the races. So IL over VS is just equal to, so 1 over ZL is 1 over LS times the result from before, which was LS over RLC S squared plus LS plus R, right? The LS's cancel, and we're left with 1 over RLC S squared plus LS plus R. That's our answer. So we can leverage the other solution here for a variant on the shortcut, right? And now we're going to use another possible way to find IL over VS, which is to say transform the source. If we transform the source, it's going to become a current source, right? And we can lump in this R with it, so a voltage source in series with a resistor or an impedance of any sort is equivalent to a current source in parallel with that same impedance. And then we're going to have 3 impedances in parallel with a current source, which is exactly a current divider, right? So we're going to apply that. So I'll redraw it though. I know, pictures help. So we have transform the source. So we're going to have some current source now. And I'm just going to call it IE. We're going to get rid of IE. We don't want anything in terms of IE in the end, right? If you wanted to know what it was, you could solve for it, but we don't care. We're just saying, oh, you can turn a voltage source in series with an impedance is just like a current source in parallel with it. And so we are going to use it for just a moment. In series with R, right? Or in parallel, I should say, with R. And then we still have the rest of the circuit, right? So what we did is we took this section here and we turned it into a current source in parallel with the resistance. So we have now C and L in parallel with that current source, right? So C and L. So this is exactly a through variable divider, or in the case of electronics, a current divider, right? So a current divider has a nice formula for the transfer function, or for the current through any of its branches, right? So we want to know the current through L. So we can write down that IL is equal to, using the current divider rule, so going back up in this lecture to this is going to be, instead of F, the generalized through variable, it's going to be I, right? So IL equals, and then we've got our impedances. So our impedances are going to be, so it's 1 over ZL divided by 1 over ZL plus 1 over ZC plus 1 over ZR. And all of that is multiplied by the in current, which is IE. So let's go ahead and simplify this down. Let's drop the, let's just plug in our impedances and then see how we want to simplify from there. First, let's divide both sides by IE. We don't want IE in the end, but we do know that we can transform that back to VS, which is what we're going to try to do at the end. But for now, let's simplify our right-hand side. So 1 over LS in the numerator divided by 1 over LS plus CS, right? 1 over CS plus 1 over R. So I would say probably dropping the LS downstairs is the way to go for simplifying this. And then multiply the numerator and denominator by R also, because we've got this fraction in R in the denominator. So I want to say R remains in the numerator, and then rearranging R times LS times C times S is RLCS squared, plus the R's cancel, so LS, plus the LS's cancel, so we're just left with R. Okay, so we've got the transfer function from IE to IL, which is interesting, but we actually want the transfer function from VS to IL. But we know that our equivalent source, IE, when we did this, we know that IE is just equal to 1 over ZR times VS, right? That was our Thevenin equivalent source, and we can transform back and forth with that impedance formula. So if I go back Oh, it was the last lecture, wasn't it? It was the lecture before this that we did the Thevenin equivalent. But remember, there's the transformation between the Norton and Thevenin equivalents, and it's essentially going through that impedance, right? And that's what we're doing here. We're going through that impedance. So we're going through that impedance ZR. So IE is just equal to VS over ZR. So we can plug that in. So we get IL over, plugging in IE equals 1 over ZR times VS equals the same thing, right? R over RLC S squared plus LS plus R. And the left-hand side, multiply both sides by 1 over ZR, which is just 1 over R, right? That cancels this guy. And then it also cancels that guy. So we get IL over VS equals 1 over RLCS squared plus LS plus R.
So why did the R, the single R, stay in the denominator when you did this step? That one.
This one?
So you multiply by LS, right, to cancel out the LS in the numerator, and it cancels out the LS in the bottom, and it gives you an LCS squared. And then you multiply through with R, right, to give you RLCS squared.
Ah.
Shouldn't that one go to 1?
Mm-hmm. Yeah. Where did I screw up? Because this is the same as that. Let's see.
This is why you don't skip steps in algebra.
This is where you don't skip steps, guys. But we would be here just doing algebra all day if we didn't skip steps. What did I do? LSCS 1 over R. You're right that this is a 1.
Isn't that the 1 over LS became your R?
Oh yeah, you're right. So the R, 1 over R turned into
LS.
into
They switched places.
yeah, exactly.
Okay.
Yeah, so the R got canceled. Thank you. I was like,
They just flip flopped back and forth.
yeah.
And turned into
So I
one.
switched order of them, and I did like 3 algebra steps.
Okay.
But yeah, thank you for keeping me honest. I mean, you definitely had me going there for a second that I had totally screwed this up. Whew! I started to sweat a little bit, Aaron. You got me sweating.
Well, I didn't.
Those 14 flights of stairs that got me up here kind of started it, but I just kept it going. Okay, so I hope that I realize that when you see this stuff happen, when you see these problems worked out, it sometimes feels a little bit like magic, but I just like knew where I was going and I just like wrote down the right formulas. And that's how anything that is sort of by inspection, that doesn't follow a specific algorithm always looks. So I actually really believe that this is an easier process than going through the full algorithm of lecture, what was it, 5.3, I guess it was. The full algorithm of 5.3, it's nice because you can teach your computer to do it, and you could just, be right every time, don't have to do any interpretation, right? But if you don't want to go through all the algebra, it sort of depends. For the computer, 5.3 is easier, right? It's an algorithm, same every time. For a human, I think that this solution process, 5.5, is a little bit easier because you don't have to go through quite as many algebra steps, typically. Sometimes there's like a break-even point where like you'd have to get so creative with all your divider rules that you might as well just do the whole algebra problem. So it kind of depends. Okay, any questions on this example? So I guess the takeaway is that IL over VS, no matter which way you go, this way from part B or this way from part C, should be the same. And so we use two different ways to get to that. And it's not like this preferred way. Either way would be fine. So, okay. I guess I would say my own personal preference is not to transform the source unless I have to. Because transforming the source, then you got to transform it back. And that just seems like a lot of work. This is a shortcut. I don't want to do extra work on a shortcut. I want to do less work. So. Okay. That is chapter 5. So I want to move on to chapter 6 if there are no questions. That should get you through your homework. I mean, you could have done the homework with all of 5.3 methods the whole way, but I think 5.5 is a little better.